that we have the applied force Fa, that friction will be Ff or Fr. Tension will sometimes be given the capital T for tension or Ft. And the net force is the sum of all the forces. A lot of times we see it written like this with the sigma F or F net. So all of them are just, I like to keep it the same to where FA, FF, and FT is what I typically use. But we could give any letter as long as we describe a decent amount what it is and we relate it back to how the problem's written, I think we'll be okay. And so what are we talking about even? We're talking about when we draw these arrows on these boxes. Sometimes you see N for normal force. I'll probably end up calling it FN. You see W here. I'll probably call it FG. FF and FA. Those are the abbreviations that I will typically take. Okay? And so when we see them, we have a frictionless surface. You'll notice that we have a couple of steps that we can take to start our free body diagrams. We're going to add all the forces in the X and Y direction. We're going to see what works horizontally, which is independent than what acts vertically. We're going to add up all our forces, okay? And if the sum of the forces is 0, then there is no net force, right? Which means also that there is no... There could be movement. No change in movement. No acceleration, right? No acceleration. Which is change in speed or velocity. And then also one more word that there is. It is at equilibrium. A hockey puck just sliding off of frictionless ice or something like that, and it's just sliding and sliding and sliding and going and going and going and going forever and ever and ever if it was really frictionless. Well, that could be at equilibrium. But it's still moving, okay? So it's not speeding up, it's not slowing down. Yes, something that is not moving is also not speeding up and not slowing down, so therefore we do know it's balanced. And we also look at the X and the Y. So, for instance, gravity pulling... Wait, which way does gravity go? Down. And then we have this table holding it up. This box with gravity pulling down at 20 kilograms at 9.8 meters per second. We'd multiply them together and get 196 newtons down, right? And, but does it sink through the earth? No, we've got this thing holding it up. So I bet you for this problem, if I was worried about the force in the Y direction, that would be 0. So then what is the net force? The net force, what do I have to worry about? Not the Y direction, but the force in the X direction. So then I would list all my force in the X direction. What do you see in the X direction on this diagram? Yeah, the force applied is what I would say. Force applied. And the force applied in the X direction is what I'm going to be worried about. And so even though we would think that it starts off with 50 newtons, I'm worried that the force applied in the X direction is actually just 50 cosine 45. Good. And so the net force is 30, I don't know. I don't have a calculator. 36 something? 37 something? What is 50 cosine 45? What's root 2 over 2 times 50? 1.7, so it's 30 something. Wait, you have a calculator?
35.
It's not just, it's 35.36? 35.35? I feel like we're rounding the wrong direction.
35.36.
Okay. I was like 3535. I would have remembered if it was repeating like that. Okay, 35.36 newtons. That's 50 cosine 45. Okay? It's not moving up and down. It's only moving side to side. And this is the only thing that's moving it side to side. So that's how we got our force. All right? We didn't have to find normal to do that. We didn't have to find gravity to do that because those are just straight up and down. We could, though. We'll see that later on. All right. Sample 1. Austin needs to pull a cart to the right, full of water, with a mass of 12 kilograms from the cross-country team. He exerts a force of 23 newtons on the handle, which is parallel to the ground. The runner from an opposing team pulls on the cart in the opposite direction for 15 newtons. So here's my cart on the ground. And the pull is parallel to the ground. And how hard did Austin pull? So the force of Austin is 23 newtons. And then I'm going to draw this about 2/3 as big if I wanted to draw it to scale. And the force of, let's call him the enemy, is 15 newtons. I don't like saying opposition because, like, O is a weird letter to give something. It conflicts with the way we write 0 and O and how they look similar. And so I'm just not a big fan of labeling things with a O sometimes. Is that all the forces that are acting on this item?
Gravity.
We have gravity.
Then we have force normal.
And then we also have a normal force. The ground that holds it up. All right, draw the free body diagram and determine the acceleration. So to show our work properly, is this moving in an up and down direction or a left and right direction? Okay, so I'm going to say that I need the net force in the x direction to talk about how it's moving. And the net force in the x direction is equal to, what kind of arrows do I have left and right? Yeah, you're right. I have FA and FE. Technically, we're looking for the sum, so we're adding them together. But if I said that it's a vector sum with arrows on top, then I could say plus. But once I take into account the arrows, the FA is going in a positive direction in the direction that we're measuring. And so I said just FA minus FE because I've already taken into account the direction when I do this. So that's where my negative came from. What's a better way of saying where my negative came from? Let's look at our picture. What can you tell me? Why the negative sign?
Because it's moving in the opposite direction from the direction we're coming.
Bingo. They're opposing each other, right? These two things go in opposite directions. That's it. All right. F of x. Wait, we have these numbers. This is just 23 minus 15. That's what you said earlier, right? So 8. F x equals 8. The net force in the x direction equals 8. Is that what they asked us for? No, they asked us for the acceleration. So F equals ma. And the mass is 12 kilograms. And the net force is 8. And we're looking for A. So we have 2/3. A equals 2/3 or 0.67 meters per second squared. If you're watching the video, I'm bobbing my hands. Part B. We need to determine the normal force, too. So to determine the normal force... Wait, that's just the same as... Wait, what is the normal force going to be equal to?
Gravity.
Okay, so we need to claim that by saying that the net force in the y direction... So we have the net force in the y direction equals the force of gravity minus force normal. And then that this is 0. Right? So 0 equals force of gravity equals force normal. Force normal equals force gravity. That's all I'm trying to say, right? Wait, force of gravity is just mg. What's mg? 12 times,
9.8.
as long as we're on Earth, 12 times 9.8, or the 9.8 exists. 12 times 9.8 is 117 point. Six. Cool. Force 117.6. That's the what is that? Force normal. Newtons. Up. How come I probably won't take points off if you leave off the direction? Well, I would have taken off points if you didn't have the plus or minus earlier. How come I won't take off points now? More than implied. What did you do? You drew a picture. So as long as you have a picture, you already have it shown in your work. Got it? That makes it a little bit easier. As long as you've got the picture, I'm less worried about the direction. Unless that direction is an unlabeled angle. You need to make sure you have your directions labeled, type of a thing. Right? So, problem 2. Hannah pulls a 10 kilogram mass with a force of 65 newtons at an angle of 30 degrees. The force of friction equals 25 newtons. Draw a free body diagram. And then it tells us to draw a free body diagram again. I only need one free body diagram. Okay, I know it says it twice. What goes on with the free body diagram? Tell me what to draw.
A box with and then we make a line going down to represent gravity.
So we have gravity going down.
Yes.
All right, Shafi, pick the easy one. Somebody else. I need 3 more arrows. Okay. 65. I get what you mean by northeast. So 65 newtons at an angle of 30. This is going to be 30 above horizontal. It doesn't tell us which way Hannah's pulling it. We just know that it's pulled that many newtons at an angle of 30 degrees. We need 2 more. We have the normal force. We don't have the normal force, but we can draw it. And then friction. And friction just goes straight back and slows us down. Force friction. All right, so we have our 4 forces. Draw the free body diagram and determine the acceleration. Is the acceleration an up and down or a side to side issue? Is it going to fly off the table, fly off the ground? Nah. I think it's heavy enough to stay there. I don't think Hannah's pulling it hard enough. So it's a side to side issue, right? So the acceleration, F equals ma. We're going to say that the net force is in the x direction that I'm worried about. Equals, wait, what goes side to side? The force applied. Is it the whole force applied?
No.
So force applied in the x direction, that's facts. Minus friction. I'm glad somebody got the joke. Thanks for laughing. Makes me feel better. 65 cosine 30. Cosine? Yeah, cosine. That's adjacent to it, so it's how much it's pulling side to side. Minus 25. So the net force in the x direction is, that's like 60-ish. Then this one is like 25. So I got like 30. Is this one where it's 31? 31.3. Yeah, 31.29. I agree. 31.29 newtons. It didn't ask us for the force. It asked us for the acceleration. So that's why I wrote F equals ma earlier. So if F equals ma, we have 31.3-ish, 31.29 equals 10 kilograms times 9 point, times A. We're looking for A. It's moving side to side, not 9.8. And so our A equals 3.13 meters per second squared. Left to right, in the direction whichever way hand is pulling. I have no idea. Okay? That's why the picture, just as long as you have the picture, I'm less worried about the direction. Okay, you could have drawn this flipped a mirror image. I'd still take it. Wait, that's only part A. Part B. Let me switch colors to part B. Part B, how far will the mass travel in 5 seconds? Uh-oh. That doesn't sound like forces. I have an A equaling 3.13 and a T equaling 5 seconds. am looking for a distance. And I'm going to assume, yeah, that it starts at 0. It didn't really tell us that. I think I have to assume it, though. So, yeah, x equals VIT plus 1/2 AT squared. And then this is 0. So x equals 1/2 AT squared. Or x equals 1/2, not 9.8, 3.13. T is 5 squared. 25, 12.5, 12.5 times 3. 36, 37. Is less than 40 bigger than 36? Am I doing that right? It's what? 39.1. Okay. 39.13. I just rounding to 3 sig figs because I did here earlier. And because all these numbers were like 2 to 3 sig figs. So I didn't want to depart from that too much. What units? Meters. Of course, in the pulling direction. Or against friction. Are we done? We've got one more. Determine the normal force. Normal force. Is that a horizontal or vertical issue? Okay. So my total force in the y direction is what, and what? Okay. Force gravity is exactly equal to the force normal and the y component of the applied. Force applied in the y direction. Good. But also, what is the total force? This is 0. It's not moving up or down. It's staying flat on the surface. So I've got 0 equals all of that. If I have 0 equals all of that, why don't I just say, it's probably easier just to say force of gravity equals force normal plus force applied in the y direction. Gravity is this the 10 kilogram box? 10 times 9.8 equals force normal plus 65 sine 30. And now that we're in our unit circle in pre-cal, you know that 65 sine 30 is just 32.5. That's 1/2 of it, right? 1/2 of 65 is 32.5. 32.5. Oh, unit circle. I love it. It's the worst. 65 and a half. 65 and a half newtons. That's the force normal, right? I subtracted 98 minus 32.5. How'd you do that in your head so fast? I've done this for 3 class periods. No, the way I did it is 98 minus 33. right? 8 minus 3. That lines up way better. Gives me a 5 for me in my ones place. No. If I did this, mental math is easy. Yeah? I know it's 32.5. If I subtract 33 and then add a half, we're good. Is that the answer? And that one is definitely up. Alarms go off in my head when I read sample 3. The alarm that goes off when I read sample 3 is that this is 1.5 kilograms. Okay. My brain automatically converts that to kilograms. A force of 30 newtons acts to the left, while a force of 10 newtons pushes at an angle of negative 45 degrees. So, help me draw my free body diagram. Tell me what to draw. Square. How many lines? Wait, give me a first line. Oh, y'all are like, I'm going to take the easy one. Force due to gravity. What else is happening to this box? To the left, 30 newtons. Well, that's another easy one.
An applied force of 10 newtons moving at a negative 45 degree angle.
That's not negative 45. Negative 45 would bring me to the corner of the box. Yeah. 10 newtons diagonally that way. Should be about a third the length of the 30 newtons, but 10 newtons. That's what you're going to get, drawing-wise. Not drawn to scale. One more. Force normal is going to extend longer than gravity by however long this one is. If it's not drawn to scale, I'm not too worried about it, but I would keep it at least relatively longer than force of gravity. Determine the acceleration. Is that an up and down issue? The force in the x direction is what I'm worried about when I do this. Force in the x direction will equal two things. First thing is that F equals ma, so it'll equal ma. What's the other thing? It equals what and what?
F net equals 30 newtons. Both the applied forces.
Both of the applied forces. Force applied 1. And then in the opposite direction, force applied 2 in the x direction. $30 minus 10 cosine 45. So I think I get 22-ish, 23-ish. Huh? Cosine 45 is 0.707, so that's why I'm subtracting 7 from it. Huh?
Wouldn't it be like cosine 360 minus 45?
I'm geometrically worried about how this horizontally is leaving. And so if this is 45 degrees, it doesn't matter if I use negative 45 or if I use 215, 315.
It was, yeah, 350.
Or just 45, it doesn't matter because all I need is the side-to-side length. I already included the negative sign right here. The fact that I'm subtracting it from this and that I have the opposite direction is all that matters. And so if you look at cosine 45 or cosine 315 or cosine negative 45, you're going to get the same value. You're just going to have to fix the sign to operate with what you know. I'm operating with this triangle right here and then just use 45 degrees. It's 0.707 times 10 is 7.07. So I got 23.1-ish. No, 22.9. 22.9-ish. And that's the force. Is that the force X? The net force in the X direction is 22.9. Therefore, F equals ma. And we have 22.9 equaling, what's the mass? 1.5 kilograms times A. So 22.9 divided by 1.5-ish. 7, 2/3, 7, 2/3, 7. That's 2. 2 acceleration. 15? 15.27 meters per second squared. Left. How do I know it's left?
The free body.
It's in the directions, and it's relative to the person who headed left with that number.
Does it not matter if you use kilograms or grams for the mass of the object?
It does matter when I do F equals ma because the newtons is kilograms meters per second squared, not grams meters per second squared. So the fact that my unit is newtons for these, I need to make sure that this is 1.5 kilograms.
Oh, okay.
Yeah, or else it doesn't divide outright. I'd be off by a factor of 1,000. Determine the normal force. Wait, that's the acceleration. Determine the normal force. Is the normal force up and down or left and right? Up and down. So I'm going to list out all my up and downs. That my net force in the y direction is equal to... Uh-oh.
Gravity.
Force of gravity, that's going to go down, plus force normal, that's going to go up, and force applied of 2 in the y direction. And that goes down, right?
Yeah.
So I snuck in a negative sign for that one. I could say plus negative, but why? Waste of time. Oh, that's easy. That means our force normal equals the force of gravity plus the force applied in the y direction as I get rid of the fact that it's going down. So it's going to be positive number equals this other value. Do they give us the mass? So 1.5 times 9.8 plus
10 sine 45.
yeah, 10 sine 45, and it's, of course, root 2 over 2 is 7.07. Sorry, times 10. 0.707, so times 10 is 7.07. This is 14.6, 14.7, I don't know. And then we're going to add 7 to it, so it's about 21, 22-ish. All right, 21.78 or 27.7, depending on where you round. Newtons. Wait. How did I skip? I skipped a step. This y direction, what's the value for the y direction? 0. That's what I skipped. This is 0, so if these, I can rearrange these and move them to the other side. Right? It's not flying up. It's not sinking down into the ground. So we know that it's balanced up and down. Well, then that's what that 0 is. Okay? So it's important that I state that. Couple of things you'll notice. I always say F equals ma somewhere on my problem. If you don't put that, you're going to lose points for showing the equation. The other thing is the equation that I build is just the net force equals, and then all the partial points of the arrows that we see going this way or that way. Okay, so that's how we set it up. Once you set it up correctly, as long as we follow the algebra and pull our numbers off of the picture correctly, we're good to go. We have to get to this part. I'm going to stop the video and restart the video.